Hello everybody. In this video I'm going to blitz for you a range of important chemical reactions that you need to be aware of for your assessments. In a separate video I've looked in detail at electrolysis. There's also a video on chemical reactions with acids and alkalis. There's a video on chemical reactions involving metals. So to start off, we're going to have a look at our energetics reactions. Those are our exothermic reactions that give out heat energy during the reaction, and our endothermic reactions that take in energy during the reaction. How we show this on a graph is important. So in this reaction, I've got my reactants and my products. And in an exothermic reaction, the reactants ultimately have more energy than the products that are formed during this reaction. Remember the activation energy to get the reaction started. It is the change in energy during the equation that we are focusing on. So in this case, using this equation, the energy of the products minus the energy of the reactants, I get 2 minus 5. So my overall change in energy is negative. Remember, in an exothermic reaction, that X reminds me something's gone wrong, so it is negative. Now, in an endothermic reaction, the products have more energy than the reactant. So this time I get an S-shaped graph as opposed to the Z-shaped graph with the exothermic reactions. So my overall change in heat energy is going to be positive this time using that equation. So exothermic and endothermic reaction simply tell us about the energy changes that happen during whatever chemical reaction you are given. Now, one example of an exothermic reaction that comes up in so many different areas in biology and chemistry are combustion reactions, which means burning. And in order for anything to burn, I need a match to get it going because it's got quite a high activation energy, the fuel that I'm using. But I also need a fuel and I need oxygen for something to burn. And that's why if we take a glowing splint and it relights, that's showing me that oxygen is present. I need oxygen for something to burn. So in a complete combustion reaction, whatever fuel I use needs to be added to oxygen, and I always get the products carbon dioxide and water. And of course, a whole load of heat energy. In an incomplete combustion, there's little or no oxygen present. And in this case, I still get the products carbon dioxide and water, but in addition, I get carbon, which is soot, and I get carbon monoxide, CO. Now, this often provokes examiners to ask about what is the issues with carbon dioxide. And as we know, this leads to the greenhouse effect, which leads to global warming. Carbon is soot, which causes dust in the air or global dimming, as we often see in pictures of, for example, London or China, when there's a lot of pollution due to the traffic. And carbon monoxide, this is a very, very serious problem because it is a colorless, odorless gas, and it can lead to suffocation and death because our red blood cells would much easier pick up carbon monoxide than oxygen. And finally, very often in fuels, there's other things mixed into it as well, such as sulfur compounds. Now, sulfur compounds, when they burn, they produce sulfur dioxide. And I want you to remember that whenever you see sulfur, think about the sulfur dioxide. When the sulfur dioxide that is polluting our air reacts with the water vapor that's being evaporated, it forms sulfuric acid. And therefore the pollution issue over there is acid rain. So rather than using the word pollution, be more specific in your exams. Now, we're also reminded about the factors that can speed up the rate of the reaction. So we remember we're learning about temperature. We're giving those particles more energy. They're going to move around quicker. There's more chance of a successful collision, and therefore the rate of the reaction is quicker. If we increase the concentration in our reaction, by increasing the concentration, there's more particles present. Remember, we used the analogy of the dance floor. There's more particles, they're more likely to bump or collide with each other, and the more successful collisions, the faster the rate of the reaction. Surface area. If I increase the surface area by crushing it into a powder, what happens? There's more area for the particles to collide with the other particles, and therefore more chance of successful collisions, and the rate of the reaction increases. And finally, if I add a catalyst, what happens is the catalyst lowers the activation energy of the reaction, and therefore there's less energy needed for the particles to collide successfully, increasing the rate of the reaction. And remember, the beauty of using a catalyst is you can use it again and again. And I'm just going to very quickly remind you of the typical rate of reaction graphs. If I'm monitoring the product being produced during the reaction, I will notice that initially the reaction is very, very quick. But as the reactants are getting used up, so less products are being formed, the reaction starts to slow down. And eventually it flattens out because I've produced all the product that I can form based on the reactants that I have used in my reaction. Now, if I change the temperature, the surface area, or the concentration, I can make that slope steeper if the rate of the reaction is faster, or less steep if the rate of the reaction is slower. And the graph could also look like this. If, for example, I'm reacting calcium carbonate with an acid, and the mass during the course of the reaction of my reactants is decreasing, I will get an inverted graph like this again. Once again, the steeper the slope, the faster the rate of the reaction. But I will always, if I use a certain amount of reactants, I will always only get a certain amount of products. So it doesn't increase the yield, the amount, it simply increases the rate. Now let's remind ourselves about reversible reactions and reactions where there is an equilibrium in place. So the classic example of this is the Haber process. Now, we need to know the rules for shifting equilibrium, because there's normally a balance that happens, and we can change that balance during the reaction by changing conditions. And sometimes we want to counteract those changes. So the rules for shifting equilibrium goes like this. If you increase the temperature in the reaction, the system will do all that it can to favor the reaction that takes in that heat energy, which is the endothermic reaction. The rule for pressure is if you increase the pressure, it will favor the side of the least gaseous moles, because that will have less pressure. So to work out which side has the least gaseous moles, you look at the balancing. So on the right-hand side, we've got 1 nitrogen, 3 hydrogen molecules, whereas on the right-hand side, we've only got 2 ammonia molecules. And then concentration. If we increase the concentration of the reactants, we're going to favor the yield of the products. So in this particular example of the Haber process, the forward reaction is exothermic and the reverse reaction is endothermic. So if we increase the temperature, what's going to happen is it's actually going to favor that endothermic reaction producing nitrogen and hydrogen. Now, if we're trying to produce ammonia, we don't want that reaction to happen. And therefore, scientists use a relatively low temperature that's not too low to affect the rate of the reaction. We also use a high pressure because if we have a high pressure, it's going to favor the side with the least gaseous moles, which is the side we want that produces ammonia. And the third condition that is used in this reaction is we add a catalyst to help the speed of the reaction. And the catalyst used is iron. Now, a quick reminder on reactions of group 1 metals with water. We know that as we go down group 1, it gets more reactive. So if we take any group 1 metal, react it with water, we get the metal hydroxide, which is why it's an alkaline, plus hydrogen gas. So for example, I can substitute potassium into this general equation plus water. I'll get potassium hydroxide plus hydrogen. And don't forget, that's the fabulous one which breaks off into a purple flame and is a very violent reaction. And then a reaction we need to remember with the halogens, the group 7 elements. We remember that with the group 7 elements, by contrast, as you go up the periodic table, it gets more reactive. And we use that information when we look at displacement reactions. So for example, if I take chlorine gas and I react it with potassium bromide, because chlorine is more reactive than bromine, it kicks the bromine out the way, forming potassium chloride, and bromine is left all on its own. And that's why we start to see an orangey brown color forming. And you can apply that to any reaction involving halides. Now, the last two reactions are only in paper 2. When we have a look at organic chemistry, there's a reaction called cracking, which is where we use heat to break down large molecules into smaller, more useful molecules. So for example, we can take decane, which contains 10 carbon atoms, and we can break that down into octane and ethene. Ethene is very, very useful to us, so we're creating more useful products. And then there's polymerization. Now, poly means many. So in this reaction, we're taking many small molecules and we're creating one large molecule instead. And we do this by breaking double bonds. So over here, we've got molecules of ethene. And these ethene molecules with their double bonds, the double bonds break due to heat and this time pressure, P for polymerization, P for pressure, and you get this long chain of molecules with the single covalent bonds. Another way of writing this is by using the square brackets to show that that repeating unit is repeated n times or many times. Good luck with your revision.